Hello, welcome to Kryptonite Physics. The subject today is vector addition. To anyone that hasn't looked at this before, it can look daunting. I promise you, it is not. We are going to do top-to-tail vector addition. You don't need a calculator, all you will need is a ruler, a protractor and a sheet of paper. What is a vector? It is simply an arrow pointing in the direction of travel. Its length is proportionate to the unit being used. We are using 1 centimeter for 1 mile per hour. This arrow is 7 centimeters long, for 7 miles per hour. The boat is traveling at 7 miles per hour, in a straight line. Our first vector arrow is 7 centimeters long, pointing in the direction of travel. The tide is also running at 7 miles per hour, in this direction. We place another vector arrow on the boat. Now we add them together. Move or copy one arrow to go top to tail on the other, keeping the length and its angle, using the protractor. Draw an arrow from the bottom of the first arrow to the top of the last. This is called the resultant velocity vector. The resultant vector is showing the direction and velocity of the boat when two or more velocities are acting on the boat at the same time. Measure its length. It is 14 centimeters long, giving us 14 miles per hour in the direction of the arrow. Let's try another. The direction of the tide changes. We have 0 as our measure. The boat is not moving, because the forward motion of the boat is being cancelled by the tide. Last one. Our boat is now traveling in this direction. Place the arrows on the boat as before, then do the top to tail again. Draw the resultant arrow. Measure it. It should be 9.9 centimeters long. The boat is traveling at 9.9 miles per hour, in this direction. Just for fun, we will add another arrow, the wind blowing at 4 miles per hour in this direction. Repeat as before, adding each arrow top to tail, in no particular order. Now measure the resultant arrow. This is your velocity value, and direction. The resultant velocity is a combination of all velocities happening to one point. Imagine standing on a moving walkway that's moving at 1 mile per hour. If you stood still, you move at 1 mile per hour. If you walked forward at 1 miles per hour, you will be moving at 2 miles per hour. Walking backwards on the walkway, you are doing 0 mile per hour. You should now have a better understanding of what a vector is, how you can add one or more vectors together, what a resultant vector is, how two or more velocities acting on one point, our boat, changes the velocity of the boat, and how each velocity can act with, or, against, each other. The subject today is circular motion. This is our mass, moving in a circular motion, at the same speed, at all times. It is rotating at a constant tangential velocity. What is tangential velocity? At all times the mass is moving in the direction of the vector arrow. If we released the mass at any point, it would fly off in this direction, at a tangent to the circle. What is a tangent? An easy way to remember this is to imagine a T. The top is just touching the circle, tangential to the circle. The bottom runs to the center. The mass always wants to go in this direction, but is held in place on its circular path. So the mass will be accelerating at a constant rate towards the center at all times. This is called centripetal acceleration. What happens when in a car and it accelerates forwards? You get pushed back into the seat. In circular motion, the pushing back happens in this direction at all times. This is called centrifugal force. This is the force you would feel when on a merry-go-round. If the velocity changes for any reason, the centrifugal force will change. The subject today is rigid body rotation with translation physics. This is a lot simpler than you may first think. If you need to know how to add vectors, look at our easy-to-follow vector addition video. Top-to-tail vector addition. No calculator needed. What is a rigid body rotation? It is a physics term for a point or mass rotating about a center point. Translation. Translation, it is simply the movement of the circle's center point. We have already looked at circular motion and the effects on a mass. Adding translation or moving the rotation changes what happens to the mass. This physics works out what is happening. We are looking down on the rotation. There are two velocities to consider for the mass: tangential velocity and translation velocity. As we have done before, both velocities are represented by a vector arrow. You can see the relationship between the arrows. The angle changes constantly. All we need to do now is to add the two vectors together. One at 2 miles per hour for the tangential velocity, and 6 miles per hour for the translation. We will do our vector addition at 4 points. Using top-to-tail addition, we add the vectors. The resultant arrows at each point are our answers. We see that the mass is going from 8 miles per hour at the top, to 6.3, 4, 6.3, and back to 8 miles per hour, on every rotation. This is a constantly changing rate of acceleration. To see what is happening to the mass, we can also use this site's vector addition tool. Input the velocities for each vector. 2 miles per hour, and 6 miles per hour. A plus B, the resultant velocity is the answer for the mass rotating at the same time the rotation moving. Each velocity alone is a constant velocity. When they are both acting on our mass at the same time, the mass's velocity changes. This change is constant. We see an ever-changing rate of acceleration of the mass, going from 8 miles per hour to 4 miles per hour, back to 8, constantly. What has this physics shown us? That a point or mass, on any rotation that is moving, will never be at a constant velocity. The only point ever at a constant is the center of the rotation. Our subject today is relative motion and inertial reference frames. What is relative motion? We can say it is motion measured relative to another point. That point may be fixed or in motion. You are walking through the fair with a friend, in the same direction, at the same speed, 2 miles per hour. Relative to the ground, both of you are walking at 2 miles per hour. Relative to each other, you are not moving. If you speed up to 3 miles per hour, you will be traveling at 3 miles per hour relative to the ground, but only 1 mile per hour relative to the other person. Relative motion is measuring those differences. Look at this fairground ride. Its track is very long, level, and straight. On the track is a rotating platform, with several seats for riders, and a large perspex dome, to protect us from the weather. You and your friend, sitting together, get on the ride. The ride isn't rotating yet, it is just traveling along the track, at a constant velocity of 4 miles per hour. The ride is an inertial reference frame. If the velocity of the ride stays constant, all the riders will have the same experience as being on ride C. That is not moving at all. This is the same as you would be in a train that's traveling at a constant velocity. The ride stops, it just rotates. You are now moving at a tangential velocity of 3 miles per hour. The ride experience will be the same as on ride B. What happens when the two motions are combined, rotation and moving along the track? Your motion is now a combination of the two velocities, 3 miles per hour and 4 miles per hour. You are now accelerating and decelerating at a constantly changing rate. At a minimum velocity of 1 mile per hour, up to a maximum of 7 miles per hour. Your ride experience is not the same as being on ride B or C. You, and the people on the ride, could say that relative to each other, you are not moving. But that would not be the reality of the ride experience. If you walked to the very center of the ride, you could say, relative to you, the riders are on ride B, just rotating. Again, this is not the reality of the ride experience, for the people still in their seats. Only relative to a fixed point, outside of the ride, can you see and calculate the reality of the ride. What has this physics shown us? That the relative to position can change the math, but it cannot change the overall reality for the riders. All motion is relative, but you can change the relative to point to change the math. Only a fixed point, away from all motions, can show the true reality of what is happening. The math is not always the reality. Today we will discuss the physics of a mass on a rotation, how and why this physics is kryptonite. First you need to understand the basics of the physics involved, using simple maths anyone can do. We have a rotation, with a mass, marked in red. The red mass rotates at a constant tangential velocity, marked with the arrow. The arrow length is proportional to the velocity, in this case it's 7 centimeters long, representing a velocity of 7 miles per hour. What is happening to the mass? If we know the value of the mass, the radius, and the velocity of the rotation, we can work out that our mass has a centrifugal force acting on it, at a constant value, at all times. Most importantly, remember that the force value and direction is a constant for the red mass. Now we get to the most important part of rotation physics, our kryptonite physics. And why it is kryptonite. This is called wheel rolling without slipping. The physics name is rigid body rotation with translation physics. Search for rigid body rotation with translation, or wheel rolling without slipping. You will find tons of examples, some complicated, some simple. With this physics, you can work out what is happening to our red mass, when two movements are happening at the same time. That is, a rotation with the rotation center moving. This is the same wheel, same red mass, at the same tangential velocity. This time we are adding the forward motion of the wheel. The velocity of the wheel's center is 7 miles per hour, in a straight line. What do you think is happening to our red mass now? The same as before? I don't think so. Look at the center of the wheel, it's at a constant velocity of 7 miles per hour. Compare it to our red mass. The red mass is moving in front and behind the center, so something else is going on. It's going faster and slower than the center. It's the job of this physics to work out what is happening. How do we do that? We can use this site's vector addition tool. We can also do it by hand to get a better understanding of vector addition. Look for top to tail vector addition. All you need is a ruler, protractor and a sheet of paper. We place the two 7 cm arrows in the direction of travel, for each of the two velocities onto the red mass's position, representing the tangential and linear velocity. You add our two vector arrows together. By adding the two vectors together, the resultant vector arrow length and direction is our answer. If the arrow is 10 centimeters long, that is 10 miles per hour, in that direction. Adding the two vectors, we get the resultant velocity vector. This is the resultant velocity for each point on our mass. It changes in length and direction. That is, acceleration, at a changing rate, of our red mass. Comparing the rotation alone, to the rotation moving, we see a big difference for our mass. One is always at a constant, the other is not. Take some time to understand the basic physics, understand the difference for the mass. It's not intuitive, but it is a physics fact. This is important for the next step. Pause this video, have a break, go and look at the physics, check out Top to Tail Vector Edition. Links in the description. Relative motion. Inertial reference frames. What is an inertial reference frame? It is a frame of reference, moving at a constant velocity in a straight line, like this train carriage. Any movement or lack of movement within it, is, as if it is on the ground next to you, watching the carriage go past. The fish in the bowl moving in the carriage, are the same as they would be, on the ground next to you, watching the carriage go past. It is a fundamental part of physics and astrophysics. I can show 1,000 examples that this is true. I can show one, where it is not. The mass has changed to a brass bee. This could be you, or me, on any rotation that is moving. You now know the difference for the two rotations, one moving, one not. What happens to the mass when the wheel is placed in the carriage? Rotating at the same tangential velocity, with the carriage's velocity at 7 miles per hour. What changes? Nothing changes for the mass. It only changes for the observer. The observer in the carriage can only see a static rotation. Observer's position cannot change the reality for the mass. It only changes what they can see to calculate from. We are tricked into thinking what you see is the reality for the mass. The math changes, not the reality. According to relative motion and inertial reference frames, this physics should not exist. The center of the rotation is moving at a constant velocity in a straight line. It is, by definition, an inertial reference frame. What have we learnt from this physics? That the fundamental physics, for the rotating globe, moving around the sun, then moving around the galaxy and universe, is flawed. They are all rotations that are moving. We have invalidated relative motion and inertial reference frames. Without relative motion and inertial reference frames, none of it works. Any force acting on a mass, or you, will not be at a constant, due to your ever-changing velocity. There is a reason, in astrophysics, why they do not use rotating reference frames that are moving. The reason is, it all falls apart if they do. Pause, take a screenshot of the next 2 pages, and print them off. Go and challenge anyone who knows physics, with the information and knowledge you now have.